right, so now that we've talked about the basics of chemistry in chapter 1, we're actually going to dive into matter. That's chapter 2. And the reason we're doing that is because you may recall that chemistry was the study of matter and the changes it undergoes. So, what is matter? So matter is anything that takes up space and has mass. Now, you don't actually have to see it for it to be matter. For example, air takes up space and has mass. There's molecules of oxygen and nitrogen and all kinds of things in there. And so air would be considered matter. Now, mass. We're not going to spend a lot of time on this, but I wanted to just let you know that mass and weight are not exactly the same thing. Mass is defined as the measure of how much matter an object contains. No matter where you go, it wouldn't change. So if I'm here on Earth or I go to the moon, the amount of matter inside of me would not change. So my mass would not change. On the other hand, weight depends on gravity. So if I was to go to the moon, the gravity is something like 1/6 what it is on Earth. So if I was to weigh myself on the moon, I would weigh 1/6 as much as I do on Earth. So weight is calculated taking in a factor of gravity. Mass is something that's constant. This little pictorial kind of shows it. So the unit for mass is kilograms. That's the standard metric unit. Or you may hear that converted to like grams or milligrams or micrograms if you're talking about tiny, tiny, tiny amounts. So my weight on Earth would be 50 kilograms. But my weight on the moon would only be 8 kilograms because the gravity is less on the moon. Typically, pound is a unit of weight, but not a unit of mass. My mass would be the same whether I was on the Earth or the moon. And technically, the unit for weight usually is newtons. This is more of a physics concept, but I just wanted to touch on it very briefly. Okay, so we can describe the properties of matter as intensive or extensive. So extensive properties depend specifically on the amount of matter in the sample. So really we're just describing how much you have. It doesn't really tell you anything about the inside, anything about the matter itself, but yet it's only giving you, think of external properties. So how much it weighs, or its mass, its volume, its length. These would all be examples of extensive properties. Honestly, in this chapter, we're focusing on intensive properties. Intensive properties are all things that would depend specifically on what kind of matter you had. So if I had 5 grams of gold, the extensive properties would be 5 grams, how much I had. It could be gold or it could be silver. The extensive property would be the same. But the intensive properties of gold and silver would be very different. We know that they don't look the same. Their density is not the same. They don't melt at the same temperature. So intensive properties would be things like hardness, odor, its density. Now density can throw people off because sometimes people think of density as an amount, but density is actually a ratio. We're going to talk more about it in our next chapter when we start talking a little more about how we use numbers in chemistry. So for example, the density of water is 1 gram per milliliter. And the density of aluminum is 2.7 grams approximately per cubic centimeter, which is sort of the same thing as a milliliter, but usually we think of milliliters for liquids and cubic centimeters for solids. So aluminum is more dense than water. And that is something that's not going to change. It doesn't matter how much water I have. For every milliliter of water, it's going to weigh 1 gram. So if I have 10 milliliters of water, it'll weigh 10 grams. If I have 10 cubic centimeters of aluminum, it'll weigh 27 grams. So that ratio would never ever change. And that's why density is an intensive property, just like boiling point and melting point also. Water has a specific boiling point. It boils at 100 Celsius. It freezes at 0 Celsius. Ethanol or acetone or other things have different boiling points and melting points. All right, now types of matter. So matter can sort of be split into substances, and this would be, we also would call these a pure substance, And this would be matter that has a uniform and definite composition, meaning it would look the same throughout, and it would always have the same ratio of elements in it. I'll show you some examples. Every sample of a given substance would have identical intensive properties because every sample would have the same exact composition. Pure water, that would be an example of a substance. Pure gold would also be a substance. It doesn't matter where I get it. If I tell you I have pure gold, it's going to be the same anywhere across the earth. It's going to be made of the same exact types of atoms. It's going to have the same properties. If we think about an example of this, let's look at gold and copper. So we did this in class and we talked about some of the differences between gold and copper. So some of the things they had in common, they were both shiny. They were both metals. They're both solids at room temperature. Some of the differences we talked about, they're not exactly the same color. They actually don't have the same melting point. Pure copper will scratch the surface of pure gold because copper is harder than gold. Gold is very soft. That's why they don't make jewelry out of pure gold. It would be very expensive, but in addition to that, pure gold is super soft, so it wouldn't really hold its shape. And so they make 14 karat gold, 10 karat gold, and that strengthens it. Another example, copper is a better conductor of heat than gold. So if I wanted something like copper-plated pans would heat things better, for example, than gold-plated pans. And of course, they would be cheaper too. So just some examples of differences and similarities in intensive properties. Now, a substance can either be an element or a compound. An element could be made of atoms, or an element could be made of molecules. So this is a molecule of oxygen. It's written as O2. But it's still a single element, right? If you look at the picture here, they're all oxygen atoms. They just happen to be found in nature joined together. Other elements are found individually as separate atoms like argon, which is a noble gas. A compound, on the other hand, is made of two or more different kinds of atoms. So unlike O2, which is made of only one kind of atom, CO2 would be a compound. This would also be a molecule, by the way. So a molecule technically could be just an elemental molecule where it's just made of a single element, or it could be a compound. But a compound is always made of molecules, and a compound is always going to have a specific ratio. This, on the other hand, is a mixture. It's made of multiple different kinds of atoms and molecules. And this would be an example like air. So let's go in a little more detail into this. So the simplest form of matter are elements. Elements can't be broken down into anything smaller and still keep their properties. In other words, if I take an atom of gold and it has a specific structure with, protons, neutrons, electrons, I can't break that down any further and still have gold. If I take away one of the protons, it actually isn't gold anymore. So the smallest thing I could have that would keep the property of being gold or silver or whatever would be an atom. We represent atoms by chemical symbols. They're usually 1 or 2 letters. We don't have enough letters to have every symbol just be a single letter. So for example, C is for carbon, but then we do Ca, and that's calcium, or Cu, and it's copper, or Co, and it's cobalt. If it is 2 letters, only the first one would be capitalized. So for example, Ki, 2 capital letters, that would not be an element on the periodic table. That would be a compound that's composed of 1 potassium and 1 iodine. On the other hand, Cl, that would be a single element. Notice how the L is lowercase. That would be chlorine. Now, some of the symbols don't match up with the names. I'm sure we talked about this actually on the pretest. They come from Latin names. So sometimes, like natrium, you'd think, why isn't it S or SO for sodium? Because that's what we call it. But it originally came from Latin natrium. And so some of the symbols don't necessarily match what you would think. For example, K is potassium, or AU is gold. And it's because the symbols are coming from their original Latin names. Now, compounds, on the other hand, are 2 or more different elements. So H2 or O2 would just be an element. They would be molecules. They would be molecules, because a molecule is, if it's two or more atoms hooked together, that is a molecule. But they would still be elements, and they would not be compounds. So H2O would be a compound, and the ratio has to stay the same. If I write instead H2O2, that's not water. That's actually hydrogen peroxide. It has to be H2O to be water. And if I have more than one, I put a number in front. So I wouldn't write at this two H2Os. You would never write that as H4O2. That would mean that you have literally two oxygens, O, O, and somehow you have four hydrogens, which this isn't even possible, but you have four hydrogens somehow connected to that. That's not what is happening here. So it always has the same formula, and if you have more than one, you just put the number in the front. We'll learn more about that later. So these are represented by specific chemical formulas, and we use subscripts, which are these little numbers, to show how many of each element are in that specific formula. So this is one from biology, glucose. You may remember it from cell respiration or from photosynthesis. So it is made of 6 carbons, 12 hydrogens, and 6 oxygens, always. So you could be asked, how many hydrogens are in a glucose? And you would be given this formula. All you got to do is look at the subscript, and that's going to tell you how many. A little more about compounds. Again, the properties of compounds are different than their original parts. For example, hydrogen is a gas, and it's an explosive gas. Oxygen is also a gas. It's a flammable gas. But when you put them together, you get water, which, as you know, is a liquid that's super important for life. Another really obvious example of this, sodium. Sodium is an explosive metal. If it touches water, it literally bursts into flames. And chlorine, that's what you see in it, what you smell in pools. It's actually a green toxic gas. But put them together, sodium chloride, this is salt. This is what you put on your French fries. So when you combine elements into compounds, they completely lose the original properties they have, and they take on a completely new set of properties that are specific to that compound. Another thing is, compounds can't be broken down physically. In other words, I can't just take a filter, pour some water in there, and then have that filter out the oxygen from the water. Water is going to stay water. You can only break compounds down by some kind of a chemical reaction. I could add electricity to water, and I could break it into hydrogen and oxygen, but I can't separate it just by, say, filtering it or something like that. So physically, I can't break it apart. They can only be broken down chemically through a chemical reaction. All right, physical properties are properties that we can observe without changing it into something else. So this would be things like hardness, color, whether it conducts electricity. Malleable means sort of how flexible it is. Its boiling point, remember that is specific. Those are physical. So they're a quality or condition that can be observed or measured without changing the substance into something new. Even if I boil water or I melt ice, I just go from solid water to liquid water to gaseous water, it's still H2O. When I boil water, it doesn't break into H and O. So this would be examples of physical properties, and when you do something like boil it, that's called a physical change. I'm not changing it into something new. I may just be changing what it looks like. Now, there are 4 states of matter. We're going to just run through three main ones. So again, here is a state change from solid to liquid to gas, and see how they're still water molecules. They just go from being very attracted to each other to now being able to slide past each other, and finally to having no attractions at all and being super spread out. So I'm going to stop there, and in our next lecture, we're going to talk in a little more detail about the properties of solids, liquids, and gases, and I'll mention plasma as well as one other type of matter that we don't really talk about in here, but it is a state of matter, so I'll mention that. And then we're going to go into chemical changes, what happens in a chemical change.